Hello everyone, I'm Chloe.
I'm Hugo.
And we're co-team leaders and co-builders of Group 19 for the design module.
The organizational part of the project, we had to keep a document to keep everything clean, and I think personally that it was key for the success of the team. And in this document we arranged these weekly meetings and the milestones we had to achieve and complete in order to be on track and to get the best possible grade.
Hello, my name is Jose. I have been the general engineering designer for our group. So I've been the one taking care of all the CAD, which started with a very raw idea of what I first thought of, which actually had 8 arms, our scarecrow, at one point.
2 on each face of our body. Now, the thought behind this was that we wanted to make sure that there wasn't any angle or direction that a bird could come from and not be scared away.
I've also played a lot with the idea of the base and how that can be done in a more efficient way, to the point where we've landed on a design that doesn't actually have a base technically, because we have a spine that goes through the whole body and sticks right into the ground. Again, less materials.
I want to draw attention to a few things about our design and how it functions. The first of which is this hole in the side of the body that allows the arm to move up and down, but comes with an important effect that we had to account for in the fact that it obviously gives water a path to go into the body of the scarecrow. This is why we chose to include this spine of ours, which can be seen in this cross-section to run through all the way from the head of the scarecrow, through the body and out the base, out the bottom. In the head is where our most valuable electronics would be held, as well as inside the body, glued to the walls, but above this line at which the hole in the body begins, because water will not be able to flow through and come up because of gravity. Wires will then come down the spine and out to the arm, where the servo motor will be housed and attached to this small extrusion you see here in yellow. At that extrusion is how the servo motor will be attached to the arm and where it will apply the torque to rotate the arm. Similarly, we will have a servo motor attached to this extrusion in the head, which will apply the torque on the whole body to rotate in this direction. As you can see, this block here represents the size of the Arduino, just for modeling purposes to see that everything fit together.
So for the builders part, we need to divide the task with the other fellow members of the team, but we started with picking the materials. We wanted something acrylic based for water resistance and wind, so we removed wood out of the equation and we chose the acrylic. We also picked the color very carefully. We wanted everything to be yellow. Ugo's gonna explain to you later on why. So we started with a simple box as the body. It's the most efficient, quickest and solid way to do the body of the scarecrow. And then for the head, we decided to use the same model as the body, but just smaller, where we stored every electronic components. And you might ask, how do you link the head to the body with the electronics components? The initial plan was to connect the wires with a sort of spine, and Hugo's gonna explain what didn't work and how we managed to fix it.
Yeah, so during this project we had a couple minor, not so minor setbacks. The first one being that a week before the project is due, we were told that one of our main pieces, or a piece that the whole project was built around, we couldn't use. Turns out it was a vacuum piece in the quad, meaning that obviously we couldn't drill it, cut it, or use it. And this vacuum metal piece used to be the spine for the scarecrow, meaning it connected the head to the body. Because of this, we had to drill into the acrylic base of the head, and which obviously harmed our scarecrow because it made it less waterproof, but still the main idea was that it should be waterproof. Then secondly, our arm was meant to hold on to the acrylic, to the body itself, but turns out that the acrylic was too thin. So what we did was to test the different acrylic bits, so to see if we could drill through it and connect a cable that it could sustain the arm. But after 3 different tests, we saw that it was impossible. The acrylic broke, it shattered, and the hole wasn't precise, or maybe it was too thin, it didn't have sufficient space at either side. This meant that we had to design another piece. This turned out perfectly. And finally, we had this problem with the materials, as we planned at the beginning that we would have a certain amount of material, but we obviously didn't plan it good enough, and we wanted the scarecrow to be as aesthetically pleasing as possible, and obviously that it could do its job as good as possible. But we miscalculated the materials, meaning that at last minute, we had to readapt our design, readapt our measurements 3 or 4 times to make it fit to the materials we had left.
Hi guys, I'm Ma Zhaowen and I'm the control system engineer in Group 19. Now I'm going to introduce the control system of the Scarecrow. The control logic is based on multi-sensor triggering strategy. In each loop, the system checks all sensors independently, and if any one of them detects a valid event, the scare action is triggered. To reduce false trigger, I applied basic filtering. The PIR sensor uses rising edge detection, and the ultrasonic sensor uses distance stabilization and movement threshold method. First, the PIR sensors are used for thermal motion detection. Instead of reacting to a continuous high signal, the program applies rising edge detection, which means the system only responds when the signal changes from low to high. This helps reduce repeating triggering. Second, the ultrasonic sensors are used for distance-based motion detection. The system continuously compares the current distance with the last stable distance. Only when the distance change exceeds a predefined threshold, and after a stabilization period, the motion is considered a real movement. Third, the sound sensor provides audio-based detection. The system samples the analog signal within a short time window, measures both the sound amplitude and the proximate frequency, and only consider it a valid trigger when the sound intensity is strong enough and the frequency fall within a preset range. However, due to the simplicity and physical limitation of a low-cost sensor, it's very difficult to reliably distinguish between human and bird movements. Therefore, the system focuses on responsive behavior rather than precise classification.
Hi guys, my name is Lin Wendu. I'm the EE designer.
Hi guys, my name is In-Hao Song and my role is EE designer.
The circuit design of this project is primarily based on parallel connections, allowing each sensor and the actuator to receive power and signals independently from the Arduino. In this setup, the 3.3 voltage output from the Arduino is dedicated to powering the input side components, including the 3 PIR sensors, the ultrasonic sensors, and the LED indicators. Meanwhile, the 5 voltage power supply is reserved exclusively for the servo motors, since motors require a more stable and higher current sources to operate reliably. To organize the wiring more effectively, the system uses 2 separate breadboards. One breadboard distributes power to all input devices, while the other supplies the output devices, such as the servo motors and the LED. The separation not only helps to reduce electrical noise between sensor and motors, but also makes the physical layout more convenient when installing the screen scroll.
In addition, the system is designed so that whenever a trigger signal is detected, a digital output from the Arduino is activated to supply power to the entire output side breadboard. This means that the output components only become active when a valid detection event occurs, which improves both energy efficiency and operational control. Furthermore, for certain components, especially the motors, the wires were extended to ensure they can be placed in proper mechanical positions on the Scarecrow structure. This allows the arms to move naturally while keeping the electronic control units securely mounted.
Hello everyone, I am Jerry Wen and I am the FMEA engineer.
My job was to look at what could possibly go wrong in our smart Scarecrow system. The system is controlled by an Arduino and uses sound sensors, infrared sensors, together with LEDs, buzzers, and motors. I focused on risks like false triggering, motors getting stuck, and signal loss. Then I ranked these risks and suggested improvements like sensor filtering, better protection, and wire layout. This helped make our final system more reliable and robust.
Hello, my name is Tala and I'm the Sustainable and Inclusive Engineer. From the beginning, we wanted our Scarecrow to be not just efficient at scaring away birds, but also in the way it used materials and energy. We started off with 8 arms, which wasn't exactly practical, so we scaled down to 4, better, but still energy intensive. We finally decided on 1 arm that rotates up and down while the body rotates as well. This system uses way less energy, yet it's just as efficient at scaring birds away. Sustainability is about doing the same job with fewer resources, which is exactly what we achieved. Now let's talk about materials. A big part of our process was reusing items from the recycling bin, such as acrylic boards, wood, the metal spine. Instead of contributing to waste, we gave these materials a second life in our prototype. Additionally, the blue overall is not just aesthetically pleasing, but in real life, it would be water resistant, durable, and made up of sustainable fabrics. Finally, I want to highlight inclusivity in 2 ways. On the one hand, our design is easily operatable by all, so it's simple, it's intuitive, and it's easily accessible. On the other hand, inclusivity within the group, everyone's input was encouraged, everyone's opinion was taken into consideration, we made the decisions collectively.
Beautiful! Finally!